Hello AP Physics C students, this is the second video. Alright, so this follows directly after the notes page that review the difference between static electric fields and induced electric fields. So it was Faraday who realized that you can induce an electric field by changing the magnetic flux through a region of space. He wrote his equation like this. The induced EMF, or voltage, equals negative N d phi m dt, where phi m is the magnetic flux. This really is the exact same thing as the induced EMF you had on the notes page there, which was the line integral or contour integral of E dot dl. Really, these are the same thing. We're going to box both of these versions in. We'll be using them in different situations, though. Right now, we're going to be focusing mainly on this idea of the changing flux. So just make sure we're clear on our terms here. The EMF here is the induced EMF. This is not necessarily the emotional EMF we've talked about before, although we will be making a relationship between the two. Phi sub m, again, is magnetic flux, and capital N is our usual number of turns or loops of wire. Sometimes you'll see this equation written without the capital N. I like to always include it to account for the fact the wire may be looped around multiple times. So let's review magnetic flux. Remember, flux is always a measure of how many of the field lines flow through some region, in this case an area, and it's always the dot product of the field you're looking at with the area vector. So in this case, it's phi m equals b dot a. We're looking at d phi dt, though, in the equation, so let's relate this to d dt of the dot product of b dot a, and let's really spell it out that b dot a is ba cosine theta. So anytime anything in this equation changes, Faraday is saying that we're going to induce an EMF, this strong connection between a changing something about magnetism and something about electricity. Well, this brings up the idea that there really are three different ways to change flux, because there's three different terms in the equation. Any one of those things changing with respect to time will induce an EMF. And so here are the three ways to change flux. The magnetic field can change, the area can change, or the angle can change. In other words, we can take these loops of wire and rotate them in some way, and that would change the flux. In the equation, we do have theta. Theta is always the angle between the two previous vectors, in this case between the magnetic field vector and the area vector, so it behooves us to remind ourselves how the area vector is defined, or at least how we find the direction of the area vector. And you might recall it is the right-hand rule shortcut. Just to refresh your memory, this is when there is a loop of wire and the current is flowing through the loop. You follow the current with your fingers, you stick your thumb out, and that's going to show the direction of the area vector. Specifically, it's going to be normal to the loop, but there's two different ways normal. This will get you the correct direction of the area vector with respect to the loop of wire. Okay, so let's apply this to the situation we've been looking at so far. Our usual example, feel free to draw this again in your notes. We have our movable conducting rods sitting on top of conducting rails here, which we assume are frictionless, connected through a resistor, so that if we complete a circuit, we can do something with it. We have an external magnetic field pointing into the page. The length of the conductor is lowercase l. It's moving to the right with a velocity v. So we ask ourselves, something has to be changing, right? If we're going to induce a current, which we've already seen happens, something must be changing, either the magnetic field, area, or the angle, the orientation between the magnetic field and the area vector. Well, it's certainly not the magnetic field, because it's a uniform magnetic field throughout here, and we're not rotating anything, so it must be the area that's changing. We know that we're going to get a positive side here and a negative side here, and we know what already is going to happen. We're going to get current flowing throughout, so something must be changing, so it has to be the area. So let's imagine this bar is moved over sometime later. We draw the dashed line and say it's over to the right sometime later. It's traveled through some distance delta x. We should be able to see that the area of the loop has changed, the area being the length of the conductor times the width of the loop here, and so it's really A equals L times X, and X is the thing that is changing. In fact, we've included more area, shown here by the dashed line. So here's the original area of the loop, and now we've added some extra area by moving the bar over, so we have a new area to the loop, given by L times X. Something has to be changing, so we have to look at the differential bit of area that we add by moving the bar over, such as L dx, where L is, of course, staying constant. It is X that is changing, so dA equals L dx. Let's write Faraday's law, that EMF equals negative N d phi dt. And whenever I write Faraday's law, I always like to really spell it out by writing that phi is ba cosine theta, and then pulling anything that's constant to the outside. So b is constant, cosine theta is constant. It is the area that is changing with respect to time. But we have to know the direction between the area vector and the magnetic field. So here's where the right-hand rule comes in. We already know charges moving around this way, so use your right-hand rule shortcut. Follow these charges around with the fingers of your right hand, and stick your thumb out. That will show the direction of the area vector. We should be getting out of the page, right? Your fingers follow along this way, your thumb is pointing out of the page. The magnetic field is into the page, the area vector is out of the page. That angle between them is 180 degrees. So let's put it together here. We have negative n, constant b, cosine 180 degrees. d a dt, well, L is constant. This is then just dx dt. I'll just differentiate both of these with respect to time. So this is d a dt equals L dx dt. Cosine 180, of course, is negative 1. dx dt we should recognize as being v. And wait a second, these negative signs go away and we're left with BLV. Well, of course we are. Right? Faraday's law isn't telling us anything new, it's just generalizing it to any situation. It doesn't have to be a changing area, it could also be a changing magnetic field or a changing angle, but in this case, if we apply it to the situation we've seen before, we must get the same results. And so here we have that motional EMF is just a special case of Faraday's law. Okay, so let's turn our problem set to number 6, where we're going to try another application of Faraday's law. Go ahead and read the problem. We'll be starting with EMF equals negative n d phi dt. Pause the video, get as much done as you can on your own, come back to see a solution. Okay, now first of all, you notice that part A asks for the magnitude of the induced EMF. So we can go right ahead and put absolute value bars around. Well, yes, there's a negative sign in the equation, but part A, we are disregarding it. So again, we want to see what's changing. So I like to spell it out that phi is BA cosine theta. We're differentiating this whole function with respect to time. What's changing? Well, here's this loop of wire with n turns. Here's the area vector, the normal to the loop, and outside here is the big solenoid. We're not rotating the loop. We're not changing the area of the loop. What is changing is the magnetic field produced by the solenoid. So I can take A and cosine theta out to the outside. They're constants. We're really just differentiating B with respect to time. It's a dB dt. That's the thing that's actually changing. Now we aren't actually given the information about how quickly the magnetic field changes. Instead, we're told about the current to the solenoid. So if you didn't figure it out yet, pause the video and go back and find the equation for a magnetic field produced by a solenoid. Okay, we haven't done this one in a while. The magnetic field from a solenoid is mu naught times n times I, where n is the turns per length, which is given in the problem. That's the 2 times 10 to the 5th turns per meter for the solenoid itself. We need dB dt, so we differentiate both sides with respect to time. Mu naught and n are constants, so this is mu naught n di dt, and di dt is what's given in the problem. That's the 1.5 amps per second. So from here, you should be good to solve on your own. You should be able to get the 2.26 volts. Now we get to part B, where we're holding the field steady. Now we're rotating the loop. So these loops inside are free to rotate around. We're not going to be changing the angle. Again, we start with EMF equals negative n d phi dt. We're not asked for the magnitude, so I'm not putting absolute value bars around. Once again, we're going to replace phi here with BA cosine theta to see what's constant and what's not. This time we're keeping the field constant, and of course the area stays constant, but we are differentiating with respect to cosine theta. Theta is the thing that is changing. So I put all the constants to the outside. This equation here is for the sports fans, although things may get canceled soon. Okay, so we're differentiating cosine with respect to time. We know this one. ddt of cosine theta, that's negative sine theta, so the negatives go away, but don't forget, we must do our chain rule, and we're going to have d theta dt as well, because theta is changing with respect to time. What's d theta dt? You say, wait a second, that's omega, that's the angular frequency. So we're just going to replace d theta dt with omega, we'll replace theta itself with omega t, and we can say that the induced EMF is NBA omega, that's from d theta dt, times sine of omega t, and we're going to actually go ahead and box this in. I want you to add this into your notes as the equation for the induced EMF when we get from rotating a loop in an external magnetic field. Assuming the magnetic field is constant, the area is constant, all we're doing is changing the angle. The book goes through a very similar derivation for this equation. So at this point we can go ahead and put some things in. What is omega? Well, it does say that it goes through one full rotation in 2 seconds at a constant angular speed, and so we can see that the angular frequency here is just pi. Multiply that by the time given, in this case the 1.25 seconds, and you should have no problem recovering the negative 16.0 volts. And yes, we do have the negative sign in front. We'll talk about that in just a little bit, because it never asks for magnitude, just asks for how much the induced EMF is. For part C, we want to find the maximum induced EMF. We see that this EMF is based on a sine function. We know that sine maxes out at the value of 1, regardless of what omega t is. And so really, the maximum the induced EMF could be is just all the terms in front, NBA omega. So it's real simple to put the numbers in and go ahead and solve. You should be getting 22.6 volts. Part D is about sketching a graph for this of the EMF versus time, and really we're just graphing this function, which we see is going to be a sine function. It would behoove us to know some important points here, like what the full period is, and well, you could just read it from the problem. We want to remind ourselves that period is 2 pi over omega. We put the pi in there for omega, and the period is 2 seconds, which we kind of already knew just by looking at the problem. It says it went through a full rotation in 2 seconds, so that is really giving us the period. At what time does it reach maximum? Well, you can set omega t here equal to pi over 2. We know that sine function maxes out at pi over 2 radians. You should be able to prove to yourself that we get the maximum EMF at time of 0.5 seconds. So if you haven't already, pause the video, sketch the graph with some important points, and come back. Okay, so we know the full period is going to be in 2 seconds, half a period is going to be 1 second, it's going to max out half a second. And what's it going to look like? Well, of course, it's going to be a sine function that maxes out here at half a second, minimizes here at 1.5 seconds, and we should label here as positive 22.6, and it has a minimum of negative 22.6. What's interesting about this, though, is that the voltage is changing not only in magnitude, but also sort of in direction. And so as we rotate the loop, we're forcing charges around in one direction, and then it switches to the other direction. The negative sign here indicating a change in direction for the voltage, also, which is not really a vector, it's really a scalar, but it's pushing charges the other way, which means that the current is going to start changing direction as well. We've never really seen this before. Our current is always pointing in one direction, what we call direct current, or DC, circuits. But now, this is how we get AC, or alternating current. If we have this constant magnetic field, and we just keep rotating this loop of wire, the charges will go back and forth in an alternating way. This is how we achieve alternating current. In class, when we come back together, I'll do a bunch of demonstrations to show some of these ideas of Faraday's law in one. I'm going to take a wire, I'm going to loop it around into a circle and put it near the BAM, the big area magnet, and then I'm going to tighten it so the loop area changes, and we'll see the galvanometer will register a current. In another demonstration, I'm going to take a very long wire stretched out all the way across the room, and we're going to turn it as if it were a jump rope, like we were doing sort of like double dutch, but just one jump rope at a time. We'll connect it to a multimeter, and we'll see that we're going to register a current. We're actually going to be using Earth's magnetic field, which is always present, and anytime a loop of wire rotates, even though it's not 100 loops of wire like this one is, but just one turn of wire, we can get a current to happen. Then we're going to use a smaller version of that, what's called a generator, where I turn the loop of wire inside a magnetic field, and we're going to generate enough current to light a light bulb. And then in class, we would have a discussion as to how this applies to our everyday lives. Well, we want to think about all the different ways we have of producing electricity, the big power plants we use, and what are some of the fuels we use. One of the fuels is fossil fuel, like coal, right? So we burn coal, and what does it do? Well, it just creates heat. And what does the heat do? It actually just boils water. That's all it does. And that boiled water, the steam, is then channeled through tubes to a turbine. And the turbine really just connected through a system of gears to a loop of wire that's sitting in a large magnet. And really all we're doing is turning a loop of wire inside a magnetic field, and that generates current. The energy is then stored in capacitors, and then it's distributed, and that's really one of the main ways we do it. Other power plants use nuclear fuel, right? We have a nuclear reaction that produces a lot of energy. You know what that energy does? It boils water. That's all it does. Same deal. The steam is channeled to turn a turbine, which turns a loop of wire inside a magnetic field. Think about other ways of generating electricity, like a windmill. You can literally see the wind pushing on the blades of the windmill, which is actually just connected to a loop of wire inside a magnetic field. So all it's doing is turning it, generating electricity, just like in this problem. If you think about geothermal, the heat produced by the Earth is then just channeled to boil water, to channel the steam, to turn a loop of wire inside a magnetic field. Really, basically, any way you can think of that we produce electricity is based on this idea of turning a loop of wire inside a magnetic field. The only one we really can't link to that is solar power. And later on in the year, I will come back to that idea and show you how solar power works. But really, all of our modern conveniences are based on this idea, or at least a lot of them are. An easy way of distributing electricity is really just a matter of turning a loop of wire inside a magnetic field, generating electricity.